Hey guys, welcome to another episode of Tool of the Week. So this week we're going to be taking a look at mathematical optimization. Now, mathematical optimization isn't a software engineering tool per se. Nonetheless, I do think that it's really important for most software engineers to have this tool in their toolbox. The reason being that mathematical optimization is extremely prevalent in artificial intelligence, which is of course a field that a lot of software engineers work in. So that's why I think it's important. Now in this video, we're going to start off by presenting a brief overview of what mathematical optimization is, which should tell you when you should use it and why you should be using it. And then I'm going to cover the common cases of mathematical optimization. For each one of the cases, we're going to create a plan, and then we'll actually execute our plan and solve the case by using Python and SymPy. After we go through these common simple cases, we're going to talk about more advanced mathematical optimization topics. Now, for the more advanced topics, we won't go in detail. We won't be executing any code for it. But the idea is that you're going to gain a solid high-level understanding of these advanced mathematical optimization topics, such that you're able to subsequently build upon it easily by doing your own research. So let's just go ahead and get started. Hey guys, welcome to another episode of Tool of the Week. This week we're going to be taking a look at mathematical optimization. So first of all, what is mathematical optimization? Mathematical optimization is basically finding the best case scenario in a specific situation. So your outcome depends on a bunch of variables. You want to find a set of variables that gives you the best outcome. So real quickly, a couple of prereqs. These aren't really stringently required, but they would help you understand things much faster. So you should be familiar with basic math like relationships, functions, derivatives, graphs, stuff like that. Some basic Python or any understanding of basic code will help out. And then optionally, if you understand the basics of JupyterLab and SymPy, that would help out as well, because I use these two tools to demonstrate mathematical optimization. So check the videos, check the description of this video for videos on the prereqs. In particular, I have previous Tool of the Week episodes that cover these tools. All right, so real quick, what are we going to cover? So what is mathematical optimization? We're going to then, which we just discussed, then we're going to start with a simple problem of one variable. So when your outcome depends on only one thing. In other words, it's a function of one variable. Then we're going to make things a little bit more difficult by saying that your outcome depends on several things, so a function of several variables. Then we'll add constraints on those variables. So those variables have to satisfy something. And then I'll show you Wolfram Alpha and how to use this to solve optimization problems. Oops, we're not at the summary yet. Okay, so here we're just importing some libraries. Again, I cover this in my SymPy and Jupyter Lab tutorials. All of these tools that you're looking at. So we import and set up some libraries. And now let's go ahead and discuss the simplest case. We have a situation where our outcome depends on a single variable, and we want to find the value of that variable that gives us the best outcome. So in other words, we have a univariate function, a function of one variable, and we want to either minimize or maximize. Which one we want depends on the domain, right? We want to maximize it if it's a good thing, and we want to minimize it if it's a bad thing. So best depends. Anyways, so what you do in this case when you just have a univariate function, you take the derivative, right? Then you find when the derivative is equal to 0. If you find when the derivative is equal to 0, that's the flat points, right? At that point, the function kind of looks flat. Then you take the second derivative.
Because when you find the derivative, when you find these flat points, you're either at a min or a max, but you don't know which. So you take the second derivative. And the second derivative basically tells you concavity. It tells you whether you're concave up or down. If you're concave up, then that flat point must have been a min. If you're concave down, then that flat point must have been a max. I'll show you an example. So actually we do an example right here. But let me draw it out for you over here. I think it'll help you out. So if we have a function that looks like this, like a parabola, first we find the first derivative, set it equal to 0, and solve. That would give us this point right over here. Then, since we don't know that our function is facing up, maybe it's facing down, right? So maybe it's something like this. In that case, our flat point would be up here. We don't know which one of these cases it is, so we take the second derivative. If the second derivative is positive, then it would indicate that the function is concave up at this location, which means that that is a min. If it's negative, oops, I don't know why I said negative and I drew positive. Okay, so if the second derivative is negative at this point, it means that at this point we are concave down. Therefore, this point, this flat point, is a max. So I hope that intuitively makes sense. And that's basically what I have written up here. So now let's actually do it. All right, so I define the variable x, I define an expression, and then I plot that expression. And here's what it looks like. Okay, then I take the first derivative, here it is, I solve it, and I find that at x equals 5, this derivative is equal to 0. So we've identified a flat point. I take the second derivative, and the second derivative is 2, which means that it's 2 along its whole domain, which means that this entire function is concave up, which means that it's definitely concave up at this point, x equals 5, which means that that x equals 5 must be a minimum. So we've identified the minimum of this function. Okay. So now let's make things a little bit more complex. We have our outcome depending on multiple things. This is more realistic. It's really seldom in life when something depends on only one other thing. So this is a little more realistic. We have a relationship between an output and several inputs. So in other words, we have a multivariate function. What values of the inputs will give us the best output? So it's a similar plan as our univariate case, a little bit more complex. So we find the derivative with respect to each variable. We call when we find the derivative with respect to every variable and we put it in a vector, we call that the gradient. Okay, so you kind of have to be a little familiar with vector math as well. I should have put that on the prereqs. But anyways, so we find the derivative with respect to every variable. So in other words, we find the gradient of the function. Sometimes a derivative with respect to a particular variable depends on the other variables, and sometimes it doesn't. Either way. So we end up with a bunch of derivative equations, one with respect to each variable. We find values of the variables that will make all these derivatives equal to 0. So we want to find a set of points that will make this function, the rate at which it's changing, it will make it be 0 with respect to every single variable. So in other words, we want to find the point where this function is not changing at all. In other words, we want to find a critical point, or as I have been calling, a flat point. But I think textbooks normally call them critical points, so just keep that in mind. Okay, so once we find that flat point, we got to do a little bit thinking to determine if it's a min or max or something else. Here's a little hint. We can use our concavity test just like before, and we can also look at nearby neighbors, nearby points. Anyways, let's get a concrete multivariate example. So we define our variables x, y, and z here, although we don't need z. Anyways, so our function is x squared plus y squared. Here it is plotted. It looks like a double parabola, just like we would expect it to. We find the gradient. So in other words, we find the derivative with respect to every variable. So here we got it with respect to x, with respect to y. And then we solve the derivative. We set them equal to 0 and we solve them. And the point that satisfies that is 0, 0. So in other words, we know that 0, 0 is a flat point. So there we go. By solving the first gradient, we found a flat point, 0, 0. From the second derivative, we know that this point is a min. How do we know that? Well, because when I took the second derivative, it's 2. So it's concave up, therefore it's a min, just like the drawing I drew up there, remember? Okay. Now let's do here I have a little note. It's worth reading, just a little detail about SIMPy. So if you want to solve a system of linear equations in SIMPy, you use this function. If you want to solve a system of non-linear equations, you use this function. Sometimes your derivatives are not going to be linear, so sometimes you got to use this function. Okay, now let's look at a case where we do have a multivariate function, just like the example right above, but here our derivatives are non-linear. Okay. The function is x to the fourth plus y to the fourth. Looks like a flattened two-dimensional parabola. By two-dimensional, I mean like it's a parabola on both this dimension and that dimension. That's what it looks like. Okay. So we find the gradient, right? We set that equal to 0, and we find out that at 0, 0, we have a flat point, which makes sense, because if we look at 0, 0, that looks very flat anyways. All right. Then we find the second gradient. So we take the second derivative with respect to every variable, and here it is. So let's recap a little. So we found a single flat point at x equals 0, y equals 0, right? By getting the first derivative, setting them to 0, and solving the system of equations. In this case, a system of non-linear equations. How do we determine if this flat point is a min or a max or none, right? So let's evaluate the second derivative to find concavity. Well, if we plug in 0, 0 into here, if we evaluate the second derivative at this point, we get 0. A value of positive means concave up, negative means concave down, 0 means nothing. So this means that this could be basically an inflection point. It could be a point where the concavity of the graph is changing and it's neither a min nor a max. So we'll have to do a little bit more analysis to figure that out. So to rule out an inflection point, here's what an inflection point would look like, right? Let me just draw something real quick here. All right. So if our graph, ooh, that's a little too big. All right. So if our graph looked something like this, this is the flat point that we'd find. And then if we do our second derivative test on basically on this point, the second derivative is equal to 0, right? But if we look at the concavity on the left and we look at the concavity on the right and we notice that they're different concavities, we know that this is an inflection point, right? If the concavities are different, so concave down, concave up, that's an inflection point. Different concavities mean inflection point. Clearly you saw that. I'll show you the other example. If it's not an inflection point, right? If it's like that, and we look at the concavity on this side, that's positive. On this side, that's positive as well. So same concavity. So the way that you rule out an inflection point is you take the second derivative on the left and on the right. Okay? Now, once we've ruled out inflection point, we still don't know if it's a min or a max. So how do we figure that out? Well, we do a similar strategy. I'll show you. So let's say that this is kind of what our function looked like, and that's our flat point. If we take the derivative on the left and the derivative on the right, not the second, just the first. So if we take the derivative here, we would have negative. If we take it on the right, we will have a positive. If this is the case, we know we're at a min. Let's look at the other case. If we were at a max, then our derivative on this side would be positive, and on this side it would be negative. They're opposites. You don't have to memorize these at all as long as you're getting the concept, right? I know that if I have a flat point and on the left I have a negative derivative, on the right I have a positive derivative, clearly if I just draw this out, that's a min, and similar logic for the max. Again, you don't have to memorize this, just understand it, and you'll be able to Google it later and derive it yourself. So that's basically all I'm doing here in this code. I rule out, I take the second derivative on both sides to rule out an inflection point. Then I take the first derivative and evaluate them on both sides, and I find out that this is a basically a min. Okay. So this is a very famous problem. Now we're getting into constraints. Now we're saying that these inputs must satisfy some condition. This is a very classical one, right? You're given a perimeter and you want to find the width and length that maximizes area. So we know that area is length times width. We know that perimeter is 2 length plus 2 width. We can basically reframe our width in terms of the perimeter and length. And now we just have a function of one variable. You have a univariate function. This is a really classical textbook problem. Just put it there really because it's trivial and it's the most trivial case of a constraint optimization problem. But here are the more complex and more realistic cases, right? You can't just simply substitute your constraint in. So then you ask yourself a couple of questions. I should make a quick note about this. I'm not gonna go super detailed into these because this video is already getting a little bit long, and this would be hours long if I went into details about all of these methods. So I'm just gonna give you a high-level overview of them and give you some keywords and a general plan so then you can have an easy time Googling it later. Okay. So constrained optimization. Now, you know that your inputs have to have some condition or some conditions satisfied. So you ask yourself some questions. Are all of my constraints equality, not inequalities? If that's the case, then you use the Lagrange multipliers method to solve them. If some of your constraints are inequalities, then you ask if all of your equations, meaning the objective and the constraints, are linear. If that's the case, then you use linear programming. But if the objective function is quadratic, but still you got to make sure that your constraints are linear, then you can use quadratic programming. If your inputs have to be integers, you can use integer programming. This can be integer linear programming. If your basically objective function is linear, it can be integer quadratic programming if your objective function is quadratic. And also, what if you have vector valued functions? So functions that spit out more than one variable. What if you're trying to optimize them? These are more complex, but they are doable. Look up vector optimization. It's a hard problem, well studied though. And lots of solutions exist for specific cases. Just do your own research. Just know that it is a somewhat solved problem. And a final note to wrap everything up really is there are tons of different objective functions, tons of different types of constraints, but for most cases, solutions do exist. There are established algorithms for solving them. But these algorithms find local minima. Finding a global minima is a much harder problem. Let's do an official summary. I like doing a summary on all of my videos. Okay, so mathematical optimization is all about finding the best possible scenario, which is a really good thing. There are lots of different types of relationships out there, lots of different cases that you might want to optimize, and lots of different algorithms. Be aware that most of these cases have solutions, just research. And I give you 2 examples here. And last, I have another little treat for this video. Here's a little, I guess, thought path that you can follow to solve optimization problems. So if you have no constraints, you can do our derivative tests. Take the first derivative, solve a system of equations to find flat points, then do some tests to find out whether it's a min or a max. Now, if you have only equality constraints, you can use Lagrange multipliers. If you have some inequality constraints, then you got to ask some more questions, right? Are all constraints linear? They have to be. If the objective function is linear, then you use linear programming. If the objective function is quadratic, then you use quadratic programming. If your inputs have to be integers, not real numbers necessarily, then you want to use integer programming. And integer programming can be mixed with these. And that's it for this video. As usual, if you guys have any questions, I'm more than happy to answer them, and I'm pretty quick at answering them. And about this feedback, I would really appreciate feedback because I do want to continually improve the quality of my videos, and feedback would be the best way for me to do that. In particular, did I go too fast? Did I go too slow? Did I go into too much detail? Or did I not go into enough detail? Was I too redundant? I tend to be redundant, but I don't think that's necessarily a bad thing. And if this series interests you, this is a series that I really, really like because I think having all of these tools in your tool belt as a software engineer will really grow you. So if you're interested in this series, you can subscribe, and then I think you also have to click some bell icon so that you're notified when I upload to this series. That's it. Thank you for watching, and I hope to see you in another one of my videos. Bye-bye.